Affinity,
where design takes form.
Hello and welcome to another Form Affinity video, where today we discuss 3D fundamentals, the psychology of three-dimensional perception as applied to Blender. This video covers 3D theory from monocular and binocular visual cues to basic 3D elements. It does not, however, discuss specific software navigation or features. Rather, we delve into the theory behind 3D and see how it is applied to Blender's interface to give you a better foundation which can carry over into any design project or any 3D software program. Before we get started, just a quick shout out to all of you guys for supporting the channel. Received a lot of good feedback on the videos and on the Gumroad products, so thank you so much for that. So you're probably familiar with binoculars or binocular, which is two, and you may be familiar with the single lens monocular distance viewers that you can buy. Well, monocular basically means one eye, and that's the first thing we're going to cover. So if you close one of your eyes, you have certain visual 3D perceptions still intact. So that's what we're going to cover first.
Imagine polygons everywhere.
So monocular cues, some of which include linear perspective, relation and size, texture, sharpness, and clarity, interposition, or how I like to call it, occlusion, because us 3D junkies were familiar with ambient occlusion, and then there's shading. So linear perspective is, of course, some of you may be familiar with this, converging lines, like you would see it on a train track or whatnot. In one point perspective, they all go to a common vanishing point. So let's say, down here on the horizon line, all these guys run into that. So something like that. So the vanishing point for this particular scene would be somewhere along the horizon line there. So that's our VP, vanishing point. And of course, these lines, as we walk forward through this scene, we would realize that that's just an optical illusion. These lines don't actually converge. They're actually parallel. So that's one cue that tells us that a scene is three-dimensional. Another thing that we would have is relation and size. So let's say we had a person here. So we got our little guy here. Beautiful figure drawing here going on. And then we have, someone further down. Let's say he's running this way or jumping. They're smaller. So could they be a smaller person? Yeah, but usually the context reveals that they're just further away. And so things that are closer are usually bigger. So that's another cue. So, and usually it's a size and relation situation. So it might be trees or mountains. And we just know based on the certain traits that how things look further away. And that gives us an idea there. So next we have texture, sharpness, or clarity. and that can actually be seen here in the scene. You have things that are closer have more texture clarity or sharpness in the texture, and things that are farther away, you can barely even see that they have any texture at all. And this gives us an idea of what's closer and what's further away. Gives us a sense of scale and dimension. So fourth, we have interposition or occlusion, and this speaks to objects that are in front or behind each other. So let me turn this off. So if I have this Blender box in our scene here, and we duplicate it, and let me get our size and relation going on as well. So we know now, because of the way that this box sits, it's and the tangents here in relation to the box behind it, we know, and because of, you know, our familiarity with objects as humans, we know that this box is sitting in front of this one. So I could actually stick it behind here, switch these layers. Now the smaller box is sitting in front of the larger box, and we know now that this is actually a larger box because of the way that these two objects are set up in the scene here. So lastly, we have shading. This is our fifth monocular cue, and so here's an example. And in this, usually scenes are, unless you're in outer space, usually scenes are top lit, so we're familiar with things being lit from the top side. So here we've got 4 spherical objects, and we can tell that, you know, this is likely a sphere sticking out towards us, and then these appear to be dimples inside of this flat surface, but they could just be bottom lit. They could still be spheres that are bottom lit. So in this scene here, let me create a new layer. We could have, you know, a hole here in our scene, and then the back side might be lit because, you know, the light's coming this way and hitting that. So that would speak to this being possibly a hole. Conversely, if we shaded, or excuse me, lit up the top, and then especially if we put in a ground shadow, then this would seem to be like some sort of spherical object sitting in this scene. So those are shading elements that allude to things being three-dimensional, and all these are monocular cues that give us an idea of 3D space. So next we have binocular cues, and these result from the fact that we have 2 eyes, and they're a little bit different than the monocular cues. a little bit more complex, but we'll go over them briefly. So the two sort of main cues for binocular is binocular disparity and convergence. So binocular disparity comes from the fact that with two eyes, we have two separate images. So I'll give you an example here of this image. This would be, what the two eyes see left and right is they would be slightly different. So you can see an example of that if you look at this image and you close one eye and then alternate between left and right, you have two different angles, slightly different, and those help to give a sense of depth. So you can imagine, in certain professions like, fighting, boxing, or martial arts, if you're missing one of those eyes, your depth perception would be somewhat compromised. So having binocular disparity assists us in understanding depth. And then the second one is called convergence. And this just comes from the fact that, let's open up this guy, for example. Different objects in space do different things to the eye muscles, or the way the eyes react. So if you had, let's say this point in our scene corresponds to this number 3 point here. Let me move this over here. So that is our number 3 point right there, and then right here. So that's pretty far off in the distance. Let's say that's like basically right in front of that back wall. So the convergence on our eyes is not very much because we're looking at a distance. So let's say we had an object that's much closer. So let's say it's right here, and there's a little bit of a shadow down here from it or whatever. That might be right here on our little diagram. So the convergence to the object that's closer to us does, more crossing of the eyes, basically, than the number 3 object. So you can see this if you hold up a pencil in front of your face. There's much more convergence than there would be if you look at an object off in the distance. So those are a couple examples. And if you're interested in studying it further, you could look into horopter and visual disparity, or binocular disparity. So those are a couple of cues. And another good term is parallax, of course. And we didn't get into parallax very much. That involves moving objects usually. So movement can give us a sense of three-dimensional space as well. But for the most part, these cues, as well as the monocular cues, give us our sense of depth and three-dimensional space. So now that we've defined the visual cues for three-dimensionality, 3D space, let's discuss the way that Blender shows works with 3D space, and some of the elements involved with that. So first, we have to define the grid. So this, you may be familiar with this simple grid from your geometry or math class or whatnot. So this is representational of orthographic view. So let's just put that in here, orthographic. So it is a 2D grid space, and it starts at the center, which is 0, 0. So that would be right there. That's your origin. And in Blender, whenever you have a new object created, it's usually created at the origin. And an orthographic, if I had to go into foreview here, an orthographic view is your 2D view of the object. So this one here, since it's showing Y and X, we're actually looking at the top view orthographic. And you can see it here in Blender. It's actually, your top-down view. You can see the Y here and the X. And so here's your front view, Z and X, and your right orthographic is Z and Y. So the perspective view is basically all the orthographics put together in 3D space. And then the orthographic view is just like your side or front, etc. So the grid allows us to plot out objects or vertices and say where they are in space. It's just sort of a defining element of any 3D software. And so in Blender, any of these, let's say we had a point here, so that'd be positive 1 on the Y and X, so 1, 1. And one of these boxes in Blender is defined or termed as a BU for Blender unit. So if you had 2 of these filled up, it would be 2 Blender units. So, and you can change that in Blender to be centimeters, meters, etc., and that defines distance across your grid. So in the perspective view, we've got something that looks more like this. And you can see our Z as our up and down axes, which is here. And then some 3D software has Z and Y switched around so that Y is your up and down axes. But yeah, this is the way that it is in Blender. So elements of a 3D or a three-dimensional object include vertex or vertices, plural, edges, and polygons, which are planar surfaces. So what that looks like is, let's say we created a single vertex at the origin, and then another at 2 Blender units, positive Y, and then another, let's say, up here. So what is that? 1, 2, 3, 4, 5, and then over about there. So that's 4 vertices. Now let's say we connected these. So there's an edge and there and there. So together they make a single polygon. And then if we extrude this polygon into the negative x dimension, we might have something that looks like this. And that is our standard 3D object, a box, which we can see here. So obviously this one is a little bit extruded in the height, so let's just let me break down what I did. Here in Blender. So I'll grab this edge here. Move it up. So this is what we had at the origin, and we had it slightly over. So 1, 2 Blender units, right? And then it was also right about like that. So we got our, 4 vertices. Four edges, and of course our face, which are those guys. And then we extruded it back like that. And just to clarify, face in Blender is polygon. It's the same term. And so to recap, orthographic is your 2D space for different views, and the perspective is your 3D space. And now to summarize, we've got going back to our 3D cues, we've got our monocular cues, which we talked about, our binocular cues, and those are all seen or help us see our 3D world in life, but also in Blender. So take, for example, linear perspective. You can see that here with the grid turned on. All lines are, even though we know these are really parallel, they're all converging to a common vanishing point. And that's how we know the difference between our perspective view and our orthographic views. The orthographic views don't have any convergence, so we know that they're 2D representations of our object, and the perspective view with the converging lines is our 3D view. And also to summarize, we talked about grid space, orthographic views, perspective, and then also the basic elements of a 3D object, which are vertices, edges, and polygons. Alright guys, so that concludes this first video in this series, 3D fundamentals in Blender. And if you like this, there will be another part to this which will go over the various areas of the 3D software, such as modeling, lighting, rendering, and materials from a beginner's standpoint. And we'll discuss things like primitives and getting started with modeling and the various elements of texturing and lighting and how they pertain to the things that we discussed in this video. And I will leave links to my Gumroad content down in the description if you're interested in that. And we will see you next time. Thanks a lot.